Have you ever been surprised to suddenly see a hidden object appear when water is added? Let us delve into the magical phenomenon of a vanishing coin. This optical illusion is a result of light refraction. Refraction of light refers to the bending of light when it moves from one transparent medium to another. From the edge of the vessel at a certain viewing angle, the coin is not visible. This is because the light rays travel in a straight line, as there is no change in medium in the unfilled vessel and thus no refraction takes place. Hence, the light rays do not reach the eyes. However, when water is poured into the vessel, the light rays refract, bending away from the normal as they pass from water, a denser medium, into air, a rarer medium. Thus, the coin seems to have elevated from its original depth, making it visible to the eyes of the observer. This elevated depth is called the apparent depth, and the actual depth of the coin is called the real depth. This experiment beautifully showcases the fundamental concept of refraction and its effects, an essential idea used in optics, lenses, and also in the bending of a pen when dipped into water. In the previous experiment, we observed the phenomenon of the refraction of light. Now, by this demonstration, we will try to prove it. For this experiment, we will need a glass slab, a hard kind of surface, preferably a board, on which we will keep a paper. We will require a ruler and a pencil and 4 board pins. To start the experiment, we will place the glass slab on the paper and draw the boundary of it around it. We will take the vertices as A, B, C, D. Thereafter, we will draw a line which will be our incident ray. And we will extend this line in a dotted ray. Now we will take 2 points on this incident ray and we will name it as P1 and P2. We will fix 2 of the board pins in these 2 points. After placing the pins, we will keep the glass slab again. Now from the opposite side of the glass slab, we will try to see the pins on the other side. And according to this line, we will place the other 2 pins on the opposite side of the glass slab. Now we will keep the glass slab aside and we will take out the 4 board pins. We will mark these 2 points as P3 and P4 and we will circle around them to mark them. Thereafter, we will draw a line corresponding to these 2 points. This will be our emergent ray. We will draw 2 normals. We will name them as MN and we will name this normal as M prime, N prime. We have to join these 2 points. We will take it as O and X. This will be our refracted ray. Now we can observe that the incident ray and the emergent ray are parallel, but they are laterally displaced. This is because when the incident ray falls on the glass, it moves from air, a rarer medium, to glass, a denser medium. And thus, we can observe that the light ray bends towards the normal. Then again, at this surface, when it moves from the denser medium glass to the rarer medium air, it moves away from the normal again. Due to these 2 bendings at the 2 surfaces, the light rays emerging is laterally displaced with a shift. But they are parallel as the Two surfaces, refracting surfaces AB and CD, are parallel, and thus the angle of incidence and the angle of emergence is equal, thus making the incident ray and the emergent ray parallel. This demonstration also covers the principle of reversibility of a path of a light ray, which states that if a light ray follows a specific path, it will follow the same path if the direction of the light ray is reversed.
Who knew science could be so electrifying? Thanks for watching.